Okay, we're talking about digitizing audio, otherwise known as sampling. As you can see here, we have an audio wave represented by this green curved line, and we want to digitize it or convert it into digits or numbers. So what we do is we basically take these readings, so this blue dot here, this blue dot here, and here. We want to do that every so often. So let's pick a time range. Let's say we want, for 1 second of time, we want to take 1,000 readings. So every millisecond, we're going to take a reading, a sample. At 1 millisecond, we sample the wave here. At 2, we sample it here. All the way up through, say, 6, we sample it here. And these dots, if you just imagine the dots and not the line, they give you sort of an approximation of what that curved line looks like. Let's look at a different example. So here we have this curved line here represents part of a sine wave from 0 to pi. And I've taken 4 samples. There's one at 0, and then there's one here, here, and here. Now these don't really look much like the original curve. They look sort of like it, but that's because we're missing a lot of information. Between 0 and here, which would be pi divided by 4, between here and here, we're missing all of this information. We're basically stair-stepping from here, up to here, up to here. So how would we better approximate this? Well, we could change the sampling rate or how often we take these measurements. Let's go from 4, let's double it to 8. Now that looks much better. That looks much more like this curve. It's still an approximation, however. I mean, you can tell that between this point and this point, you're really not representing this information very well. You're not representing it at all. You're just stair-stepping here. If I want to actually represent it better, I need to increase the sampling rate. More of these rectangles, more samples. So let's go from 8 to 40. That looks a lot better. That actually looks quite a bit like that original curve. There's still error. If I were to increase it to, say, a sampling rate of 100, even better. There's still error, however. You can see this sawtoothy stair step here. If I were to actually represent it perfectly, I would need this infinite number of readings, which I can't get, but we want an approximation. So this is a 1,000 hertz tone, and it's sampled at 8,000 kilohertz. So 8 kilohertz, 8,000 times per second, it's going to take a reading. And you can see the dots here, what it would look like. If I were to increase the sampling rate to 16 kilohertz, it looks better. It looks like a better approximation. And 48 kilohertz looks even better. That's better than CE quality, actually. So these dots look quite a bit like that wave. They are an approximation. So what happens if, you don't sample high enough? Let's take this 1,000 hertz tone and change it to a 4,000 hertz tone. Okay, you can see that this looks less like that waveform now. You can tell that it goes above the x-axis and below the x-axis. But really, these dots here, 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 they don't really look like that wave anymore. In fact, if I were to change this to an 8,000 hertz tone, then you can see they don't go above the x-axis or below at all. And this really doesn't look like a wave. It looks like a straight line. It can get even worse than that. If I go above 8,000 with a 16,000 hertz sampling rate, both of these lines, this blue one and this orange dotted one, are representative of the samples. So you get strange artifact noise. We can hear that. Here I have a 1,000 hertz tone, 8,000 hertz sampling rate. This is what it sounds like. Okay, if I were to reduce the sampling rate to 4,000, it's still going to sound pretty good. If I go to 2,000, however, we start getting in trouble. We get some of these artifacts that we were talking about before, and you can actually see that visually here. Here's what it sounds like. So that 1,000 hertz tone no longer sounds like a 1,000 hertz tone.